Tonight, we're going to uncover something that most people never think about. But once you understand it, you will never see the universe the same way again. Every force you have ever felt, every push, every pull, the ground holding you up, a magnet snapping to your fridge, the light warming your skin, none of it works the way you think it does. Particles of matter never actually touch each other. Instead, every force in the universe is created by invisible messenger particles being hurled back and forth between matter at speeds you cannot imagine. These messengers are called bosons. Without them, there would be no forces, no atoms, no stars, no planets, and no you. Tonight, we're going to find out what they really are and why everything depends on them. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know. Force. You experience forces every single day of your life. You feel them constantly, even if you don't think about them. When you push open a door, you're applying a force. When you lift a cup of coffee, you're working against a force. When you sit in a chair, forces are holding you up. When you drop your phone and it hits the ground, a force pulled it down. Forces are everywhere. They're woven into every single thing you do, from the moment you wake up to the moment you fall asleep. They feel obvious. They feel simple. Push something and it moves. Drop something and it falls. Magnets stick to metal. The sun warms your face. These seem like the most basic and unremarkable facts about reality. Things push and pull on other things. That's just how the world works, right? But here's where it gets strange. If you stop and really think about what's happening when a force acts on something, when you really dig into the question of how one object reaches across space and influences another object, you run into one of the deepest mysteries in all of physics. And it's a mystery that confused some of the greatest minds in history. Let's take gravity as an example, because it's the force you're most familiar with. You're sitting somewhere right now, and the Earth is pulling you down. You can feel it. That pull is gravity. But think about what's actually happening here. The Earth is a massive sphere of rock and metal, about 12,742 kilometers across. You're sitting on its surface, and somehow, without anything visibly connecting you to the center of the Earth, without any rope or chain or physical link, the Earth reaches up through kilometers of solid rock and pulls you toward it. Not just you, everything. Every person, every building, every ocean, every molecule of air. The Earth pulls on all of it simultaneously, constantly, without ever stopping, without ever getting tired, without any visible mechanism. How? How does the Earth know you're there? How does it reach across the space between its center and your body and exert a pull? What is actually doing the pulling? Isaac Newton was the first person to describe gravity mathematically. In 1687, he published his law of universal gravitation, which said that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This was revolutionary. It explained why apples fall from trees and why planets orbit the sun using the same equation. It was one of the greatest achievements in the history of science. But Newton himself was deeply uncomfortable with something about his own theory. His equation described how gravity behaved, but it didn't explain how gravity worked. It said that two objects attract each other across empty space, but it didn't say what carries that attraction. There's nothing visible between the sun and the Earth that pulls the Earth along its orbit. There's no rope, no spring, no physical connection. The sun is about 150 million kilometers away from Earth. And somehow, across that vast expanse of empty space, it grabs the Earth and holds it in orbit. Newton called this action at a distance, and he hated it. In a letter to a colleague, he wrote that the idea that one body could act on another through empty space without any intermediary was, in his words, so great an absurdity that he believed no person who had any competent faculty of thinking could ever fall into it. Newton himself thought his own theory was describing something impossible. He knew gravity worked. He could calculate its effects with extraordinary precision. But the idea that a force could just reach across empty space with nothing carrying it seemed fundamentally wrong to him. And he was right to be suspicious because, as we now know, that's not actually how forces work. Let me give you another example. Electromagnetism. Take two magnets and hold them near each other. If you orient them the right way, they'll snap together with a satisfying click. Flip one around and they'll push apart. You can feel the resistance in your hands, but look between the magnets. What's there? Air. Just air. And if you put those magnets in a vacuum, they'd still attract and repel each other. Even with literally nothing between them, no air, no material, no particles at all, the magnets still influence each other. Something is reaching across the gap between them and creating a push or pull. But what? For centuries, no one had a satisfying answer. Forces seem to act through empty space, and while we could describe their effects beautifully with mathematics, the mechanism, the actual physical process that creates a force, remained hidden. Then, in the 19th century, a profound shift in thinking began. And it started with a question that seems almost childish in its simplicity. What if empty space isn't actually empty? This is where we need to introduce one of the most important concepts in all of physics. The field. A field is something that exists everywhere in space and has a value at every single point. You can think of it as an invisible structure that fills all of space, like a vast ocean that everything is submerged in. You can't see it, you can't feel it directly, but it's there, and it influences how things behave. The British physicist Michael Faraday was one of the first people to think about forces this way. Faraday didn't have a formal mathematical education, but he had extraordinary physical intuition. When he thought about magnets and electric charges, he imagined invisible lines of force extending out from them in all directions, filling the space around them. In Faraday's picture, a magnet doesn't reach across empty space to pull on another magnet. Instead, the first magnet creates something in the space around it. It sets up a field, and that field extends outward in all directions. When the second magnet enters this field, it responds to the field that's already there. The magnets don't interact directly with each other. They interact through the field. James Clerk Maxwell took Faraday's intuition and turned it into precise mathematics. In the 1860s, Maxwell published his famous equations describing electric and magnetic fields. These equations showed that electric charges create electric fields around themselves, and moving charges create magnetic fields. The fields exist in space, and other charges respond to those fields. Forces aren't transmitted instantly across empty space, they're carried by fields. Maxwell's work also revealed something stunning. His equations predicted that oscillating electric and magnetic fields could sustain each other, creating waves that would travel through space at a specific speed. When Maxwell calculated that speed, it turned out to be about 300,000 kilometers per second, exactly the speed of light. Light itself was an electromagnetic wave, a ripple in the electromagnetic field. This was a unification of such beauty and power that it changed physics forever. So fields gave us a mechanism for forces. Objects don't reach across empty space to influence each other. Instead, they create fields, and those fields extend through space and push or pull on other objects. This resolved Newton's discomfort with action at a distance. The Earth doesn't reach across 150 million kilometers of empty space to grab the Sun. Instead, the Sun creates a gravitational field, and Earth responds to the part of that field where it happens to be. But this wasn't the end of the story, because in the early 20th century, physics underwent another revolution, one even more dramatic than the introduction of fields. Quantum mechanics arrived, and it revealed that fields aren't smooth and continuous. They're made of particles. This is where things get truly fascinating and where we start to approach the heart of tonight's story. In the quantum world, everything comes in discrete packages. Energy isn't continuous, and it comes in chunks called quanta. Light, which Maxwell showed was a wave in the electromagnetic field, also behaves as a stream of particles. These particles of light are called photons. Each photon carries a specific amount of energy determined by the frequency of the light. This was discovered by Max Planck in 1900 and expanded by Albert Einstein in 1905. A field that seems smooth at everyday scales is actually made of tiny, discrete units when you look closely enough. And here's the crucial leap. If the electromagnetic field is made of photons, and the electromagnetic field is what carries the electromagnetic force, then photons are what carry the electromagnetic force. The force between two charged particles isn't just some abstract influence transmitted through a field, it's the result of photons being exchanged between those particles. The photon is a force-carrying particle, and this idea that forces are carried by particles is one of the most important insights in modern physics. But before we dive deeper into how this particle exchange actually creates forces, we need to understand something fundamental. There are two kinds of particles in the universe, and they are profoundly different from each other. Everything in the universe, every particle that has ever been detected, falls into one of two categories. These categories are called fermions and bosons, and the difference between them is what makes the universe possible. The distinction comes down to a property called spin. Now, spin in particle physics doesn't mean the particle is literally rotating like a spinning top. It's an intrinsic quantum property, something the particle simply has, like mass or charge. You can think of it as a fundamental characteristic of the particle that determines how it behaves. But here's what matters. Fermions have what physicists call half-integer spin. That means their spin comes in values like 1/2, 3/2, 5/2, and so on. Bosons have integer spin, meaning their spin comes in values like 0, 1, 2, and so on. This might sound like a trivial mathematical difference. Half integer versus integer. Who cares? But this tiny difference in spin has consequences so enormous that it shapes the entire structure of reality. Because particles with different types of spin follow completely different rules for how they can exist together. Fermions obey something called the Pauli exclusion principle, named after Austrian physicist Wolfgang Pauli, who proposed it in 1925. The exclusion principle says that no two identical fermions can occupy the same quantum state at the same time. In plain language, fermions refuse to be in the same place doing the same thing at the same time. They exclude each other. They demand personal space. This might sound abstract, but it's the reason matter exists as we know it. Think about atoms. An atom has a nucleus surrounded by electrons. Electrons are fermions. Because of the Pauli exclusion principle, electrons in an atom can't all crowd into the lowest energy state. They're forced to stack up into different energy levels, different orbitals, different arrangements. This stacking is what gives atoms their structure. It's what makes chemistry possible. It's why different elements have different properties, why carbon behaves differently from oxygen, why metals conduct electricity and rubber doesn't. Without the exclusion principle, all electrons would collapse into the lowest energy state. Atoms would have no structure. There would be no chemistry, no molecules, no solid objects, no life. The Pauli exclusion principle is also why you can sit in a chair without falling through it. The electrons in your body and the electrons in the chair refuse to occupy the same quantum states. They resist being compressed together. That resistance is what gives matter its solidity. When you push on a wall and feel it push back, that's the Pauli exclusion principle at work. Bosons follow completely different rules. Bosons don't obey the exclusion principle. There's no limit to how many identical bosons can occupy the same quantum state at the same time. You can pile as many bosons as you want into exactly the same place, doing exactly the same thing. They don't resist. They don't push each other away. In fact, bosons actually prefer to be in the same state. This tendency is what makes lasers possible. A laser works by stimulating enormous numbers of photons into the exact same quantum state, all with the same wavelength, the same direction, the same phase. Photons, being bosons, are perfectly happy to pile up like this. Fermions could never do this. Now here's where it all comes together. The fermions, the particles with half-integer spin, that obey the exclusion principle, are the particles that make up matter. Quarks, which combine in groups of 3 to form protons and neutrons, are fermions. Electrons, which orbit atomic nuclei and determine chemical behavior, are fermions. Neutrinos, ghostly particles that barely interact with anything, are fermions. All the particles that make up the stuff of the universe, the building blocks of atoms and molecules and everything you can see and touch, are fermions. The bosons, the particles with integer spin that can pile up without limit, are the particles that carry forces. The photon, which carries the electromagnetic force, is a boson. The gluon, which carries the strong nuclear force that holds quarks together inside protons and neutrons, is a boson. The W and Z bosons, which carry the weak nuclear force responsible for certain types of radioactive decay, are bosons. And the Higgs boson, which plays a unique role in giving other particles mass, is a boson. So the universe has this remarkable division. On one side you have fermions, the matter particles, the stuff things are made of. They take up space, they resist being compressed, they build structures. On the other side, you have bosons, the force carriers, the messengers that transmit interactions between matter particles. They can overlap, they can pile up, and they create the forces that make matter behave the way it does. Without fermions, there would be nothing. No matter, no structure, nothing to push or pull. Without bosons, there would be no forces. Matter would exist, but it would just sit there. Nothing would attract, nothing would repel, nothing would hold together or fly apart. Atoms couldn't form, because there would be no electromagnetic force to bind electrons to nuclei. Nuclei couldn't form because there would be no strong force to hold protons and neutrons together. Stars couldn't form because gravity would have no mechanism to act. The universe would be a formless soup of isolated particles drifting through space, never interacting, never combining, never building anything. It's the interplay between these two types of particles that makes reality possible. Fermions provide the substance, bosons provide the interactions. Together, they create everything. But now we face the central question of this entire story. How does it actually work? How does exchanging a boson between two fermions create a force? What is the physical mechanism that turns the act of tossing a particle back and forth into a push or a pull? Because this is where most explanations stop. They'll tell you that forces are carried by bosons, that photons carry electromagnetism, that gluons carry the strong force, but they don't explain how. They don't explain the mechanism. And the mechanism is the most fascinating part. To understand this, we need to go deeper into the quantum world. We need to understand what quantum fields really are and how particles emerge from them. Because particles, both fermions and bosons, aren't tiny little balls flying through space. They're something much stranger. They're excitations of fields. Imagine a calm lake. The water is flat, smooth, undisturbed. Now drop a stone into it. A ripple appears. That ripple travels across the surface, carrying energy with it. The ripple isn't a separate thing from the water. It's a disturbance in the water. It's what happens when the water is excited, when energy is added to it. Now imagine that the entire universe is filled not with water, but with fields. Invisible fields that extend everywhere, through every point in space, from here to the most distant galaxy. These fields are always there, even in what we think of as empty space. And when energy is added to one of these fields, it creates a ripple, a disturbance, an excitation. That excitation is what we call a particle. An electron isn't a tiny ball. It's a ripple in the electron field. A quark isn't a little marble inside a proton. It's an excitation of the quark field. A photon isn't a little bullet of light. It's a vibration in the electromagnetic field. Every type of particle corresponds to its own field. There's an electron field, a quark field, a photon field, a gluon field, a neutrino field, a Higgs field, and more. All of these fields fill all of space, layered on top of each other. And what we call particles are just localized excitations, ripples, vibrations in these fields. This is quantum field theory. It's the framework that underlies all of modern particle physics. It's the most precise and successful theory in the history of science. And it tells us something profound. The universe isn't made of particles floating in empty space. The universe is made of fields. Particles are just what fields do when they're excited. And forces, the pushes and pulls that hold everything together or tear it apart, are what happens when these fields interact with each other. When the electron field interacts with the electromagnetic field, that interaction is the electromagnetic force. When the quark field interacts with the gluon field, that interaction is the strong force. Forces aren't separate things imposed on particles from outside. They emerge naturally from how the fields interact. This is the key insight. Forces are not mysterious influences acting at a distance. They are consequences of field interactions. And the bosons, the force-carrying particles, are the quanta of these interactions. They are the smallest possible units of force. Just as a photon is the smallest possible unit of electromagnetic energy, the exchange of a virtual photon between two charged particles is the smallest possible unit of electromagnetic force. This distinction between fermions and bosons, between matter and force, between substance and interaction, is the foundation of everything we're going to explore tonight. It's the framework that makes the rest of the story possible. Because once you understand that forces are carried by bosons, exchanged through quantum fields, you can begin to understand how the universe builds itself, how protons and neutrons hold together, how atoms form, how stars shine, and how the simple act of exchanging invisible messenger particles creates every force you have ever experienced. The question now becomes, what does this exchange actually look like? How does a photon being passed between two electrons create the force of electromagnetism? What happens inside a proton when gluons hold quarks together? And how do the massive W and Z bosons create a force so weak that it only works at distances smaller than an atomic nucleus? These questions are where the story really begins. Because the answers reveal a universe that's stranger, more beautiful, and more elegant than most people ever realize. The mechanism of force, the actual nuts and bolts of how bosons create pushes and pulls, is one of the most remarkable discoveries in the entire history of science. And understanding it will change how you see everything around you. So now we know that forces are carried by bosons, that matter is made of fermions, and that both are excitations of invisible quantum fields filling all of space. But knowing that forces are carried by bosons and understanding how that actually works are two very different things. Saying that photons carry the electromagnetic force is a bit like saying that money makes the economy work. It's true, but it doesn't explain the mechanism. It doesn't tell you what's actually happening at the deepest level. How does one particle tossing another particle back and forth create a push or a pull? What is physically going on when two electrons repel each other? What does it actually look like at the quantum scale when a force is being transmitted? These are the questions that matter. And the answers are among the most beautiful discoveries in all of physics. So let's dig in. Let's figure out how exchanging a particle between two other particles creates a force, because this is the part that most explanations skip, and it's the part that changes everything. There's a classic analogy that physicists use to explain this, and it's worth starting there because it captures part of the truth, even though it eventually breaks down. Imagine two people standing on a frozen lake. The ice is perfectly smooth, so there's almost no friction. Both people are wearing ice skates. Now imagine one of them picks up a heavy ball and throws it to the other person. What happens? When the first person throws the ball, the act of throwing pushes them backward. Newton's third law. Every action has an equal and opposite reaction. The thrower recoils away from the direction they threw the ball. When the second person catches the ball, the impact pushes them backward too. The momentum of the ball transfers into the catcher, shoving them in the direction the ball was traveling. So both people end up moving away from each other. They've been pushed apart by the exchange of the ball. If they keep throwing the ball back and forth, continuously launching it from one person to the other and catching it each time, they'll keep moving apart. The continuous exchange creates what looks like a repulsive force between them. They're being pushed apart even though neither person is directly touching the other. The ball is the intermediary, the messenger that carries momentum between them and causes both parties to recoil. This is roughly how boson exchange creates a repulsive force. Two particles, let's say two electrons, exchange a boson, in this case a virtual photon, and the exchange transfers momentum between them. The result is that they push apart. The boson is the ball, the electrons are the people on the ice, and the continuous exchange of virtual photons is what we experience as the electromagnetic repulsive force between two negative charges. Each exchange transfers a tiny amount of momentum, and the cumulative effect of countless exchanges per second produces the steady repulsive force we measure in experiments. This analogy is useful, but it has a glaring problem. It only explains repulsion. When you throw a ball back and forth, both people move apart, but forces aren't always repulsive. Gravity pulls things together. A proton and an electron attract each other. Magnets can snap together across a gap. The electromagnetic force between opposite charges is attractive, not repulsive. How does exchanging a particle create an attractive force? You can't create attraction by throwing balls back and forth. Every throw pushes people apart. You could try to modify the analogy. Some people imagine a boomerang that curves around behind the other person, somehow pulling them forward when caught. Others imagine the two people throwing the ball behind themselves, so that the recoil pushes them toward each other. These are creative attempts, but they're all stretches. None of them honestly capture what's happening. The truth is that the ball throwing analogy breaks down at this point because the particles being exchanged aren't ordinary objects. They're virtual particles, and virtual particles don't behave like anything you've ever encountered in everyday life. To understand attraction, we have to leave the classical world behind entirely. This is where we need to embrace the full strangeness of quantum mechanics. Because in the quantum world, the exchange of particles works differently from anything in our daily experience, and it can produce both attraction and repulsion depending on the properties of the particles involved and the charges of the matter particles exchanging them. In quantum mechanics, when two charged particles interact, they don't exchange a real photon that you could detect flying between them with an instrument. They exchange what physicists call a virtual photon. Virtual particles are deeply strange. They don't obey the usual rules that govern real particles. A real photon, the kind that travels from the sun to your eye, moves at the speed of light, has a specific amount of energy determined by its frequency, and obeys all the standard laws of physics. A virtual photon doesn't have to follow these rules. It can carry any amount of energy. It can carry any amount of momentum. It can even appear to violate conservation of energy temporarily as long as it gives back what it borrowed quickly enough. This borrowing is allowed by Heisenberg's uncertainty principle, one of the foundational principles of quantum mechanics. The uncertainty principle says that you can violate conservation of energy by a certain amount as long as you do it for a correspondingly short period of time. The greater the energy violation, the shorter the time window. Virtual photons pop into existence, carry momentum and energy between two charged particles, and then vanish. They exist for such an incredibly brief time that you could never directly detect one in the act of being exchanged. They're called virtual because they can't be observed independently. You never see the virtual photon itself traveling between the two particles. You only see its effects. You see the force between the two charged particles. You see them attract or repel. But the messenger that carried the interaction between them remains forever hidden. Now, here's the remarkable thing. The mathematics of quantum field theory shows that when two particles with the same charge exchange virtual photons, the result is a repulsive force. The particles push apart, just like in the ball throwing analogy. But when two particles with opposite charges exchange virtual photons, The result is an attractive force. The particles pull together. This isn't intuitive. There's no classical analogy that perfectly captures it. It's not that the photon somehow curves around and pulls the particles together. It's that the quantum mechanical calculation, when you work through all the mathematics properly, gives you a negative sign in the force equation for opposite charges. That negative sign means attraction instead of repulsion. It emerges purely from the mathematical structure of quantum field theory. The equations tell us that the exchange of virtual bosons can produce both attraction and repulsion, depending on the charges and properties of the particles involved. The ball-throwing analogy works for repulsion, but attraction requires you to trust the mathematics and accept that virtual particles can do things that ordinary objects simply cannot. In the 1940s, a brilliant American physicist named Richard Feynman developed a way to visualize these interactions that transformed how physicists think about forces. He created simple diagrams, now called Feynman diagrams, that show how particles interact by exchanging bosons. A Feynman diagram looks deceptively simple. You draw two straight lines representing incoming particles, say two electrons moving toward each other. Between them, you draw a wavy line representing the exchanged virtual photon. The two electron lines change direction after the exchange, bending away from each other if the force is repulsive, representing the fact that their momenta have changed. The point where an electron line meets the photon line is called a vertex, and each vertex represents a specific interaction between the electron and the electromagnetic field. That's it. Two straight lines connected by a wavy line with two vertices. A child could draw it, but this simple picture encodes an enormous amount of physics. Each Feynman diagram corresponds to a precise mathematical expression. Feynman developed a set of rules that let you translate any diagram directly into an equation. You can calculate the probability of the interaction happening, the energy transferred, the angles at which the particles scatter, the distance dependence of the force, all from this simple drawing and the rules associated with it. And for any given interaction, there isn't just one Feynman diagram. There are infinitely many. The simplest diagram shows the exchange of one virtual photon. That's the dominant contribution to the force. But there are more complex diagrams. The virtual photon might briefly split into a virtual electron and a virtual positron, which then recombine into another virtual photon before being absorbed. Or two virtual photons might be exchanged simultaneously instead of one. Or the original electron might emit and reabsorb a virtual photon on its own before exchanging one with the other electron. Each of these possibilities is a legitimate quantum process, and each one contributes to the total force between the two particles. To calculate the force with perfect precision, you would have to add up all the contributions from all possible Feynman diagrams, an infinite number of them. In practice, this is impossible. But the beauty of the theory is that the simplest diagrams contribute the most, and each successive level of complexity contributes less and less. The single photon exchange diagram gives you the bulk of the answer. The next simplest diagrams give you small corrections. The diagrams after that give you even smaller corrections, and so on. In practice, physicists calculate the first several levels of diagrams, and the result is already extraordinarily accurate. The corrections from more complex diagrams are tiny, but they're real, and they can be measured with sufficiently sensitive experiments. The theory that describes all of this, the complete mathematical framework for how electrically charged particles interact by exchanging virtual photons, is called quantum electrodynamics, or QED for short. QED was developed primarily in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, who all independently worked out the mathematics from different angles but arrived at the same results. All three shared the 1965 Nobel Prize in Physics for their contributions. But the conceptual roots go back further, to Paul Dirac in the late 1920s, who first combined quantum mechanics with special relativity and laid the essential groundwork for quantum field theory. And QED is arguably the most successful theory in the history of science. Not just one of the most successful, the most successful. Let me explain why. Because the precision involved is almost hard to believe. QED makes predictions that can be tested by extraordinarily precise experiments. One of the most famous predictions involves a property of the electron called its anomalous magnetic moment. The electron behaves like a tiny magnet, and the strength of that magnetism can be calculated using QED. When you include contributions from increasingly complex Feynman diagrams, the theory predicts the electron's magnetic moment to more than 10 decimal places. The predicted value of a quantity called the G factor is approximately 2.002319304,362. When experimentalists measured the same number in the laboratory using incredibly sensitive equipment, trapping individual electrons in magnetic fields and measuring their behavior with extraordinary care, they got a value that agreed with the theoretical prediction to better than 1 part in 10 billion. Think about what that means. If you measured the distance from New York to Los Angeles, and your measurement was accurate to within the thickness of a single human hair, that would be less precise than QED's prediction of the electron's magnetic moment. No other theory in the history of science has achieved this level of agreement between prediction and measurement. Not Newton's mechanics, not Einstein's general relativity, not any theory in chemistry or biology or engineering. Nothing comes close to the precision of QED. This extraordinary precision tells us something profound. The picture of forces being carried by virtual boson exchange isn't just a useful model or a convenient way of thinking about things. It isn't a metaphor or an approximation. It's a staggeringly accurate description of how the universe actually works at the most fundamental level. When two electrons repel each other, they really are exchanging virtual photons. This is the mechanism. This is what's happening. And we know it because the theory that describes this mechanism makes predictions accurate to 10 decimal places. The development of QED was not easy. It took decades of struggle. The early calculations kept producing infinite answers, which obviously couldn't be physically correct. If you naively calculate the probability of two electrons scattering off each other by adding up all possible Feynman diagrams, the sum of all those contributions gives you infinity. The integrals diverge. The numbers blow up. This was a genuine crisis. For years, it seemed like quantum field theory was fundamentally broken, that the very framework that seemed so promising was actually producing nonsense. The solution came through a technique called renormalization. Feynman, Schwinger, and Tominaga showed that the infinities could be systematically absorbed into redefinitions of physical quantities, like the electron's mass and charge. The idea is subtle. You start with the bare properties of the electron, its mass and charge before any interactions. Then, you account for the fact that the electron is constantly interacting with the electromagnetic field, constantly emitting and reabsorbing virtual photons. These interactions modify the electron's properties, and the modifications are formally infinite. But by carefully redefining what you mean by the electron's mass and charge, absorbing the infinities into these definitions, the remaining calculations give finite, sensible, extraordinarily precise answers. Renormalization was controversial at first. Some physicists, including Dirac himself, thought it was a mathematical trick that swept real problems under the rug. But its predictions were so stunningly accurate that it became accepted as not just a trick, but a legitimate and deep insight into how physics works at different energy scales. Now, let's talk about what the photon's specific properties mean for the electromagnetic force, because the characteristics of the force carrier determine the characteristics of the force it creates. This is a crucial principle that applies to all forces, not just electromagnetism. The personality of the boson dictates the personality of the force. First, and most importantly, the photon has zero mass. It's completely massless. This single fact has enormous consequences for electromagnetism. The range of a force is determined by the mass of the boson that carries it. This connection comes from the uncertainty principle. A virtual particle can borrow energy to exist, but it has to give that energy back quickly. The more mass a virtual particle has, the more energy it needs to borrow just to exist, because mass is energy according to Einstein's famous equation, E equals mc squared. More energy borrowed means a shorter time allowed by the uncertainty principle. A shorter time means the virtual particle can travel a shorter distance before it must vanish. Massive bosons create short-range forces. Massless bosons create forces with infinite range. Because the photon is massless, it doesn't need to borrow any energy for its rest mass. It can borrow just a tiny amount of energy for its kinetic energy and travel an enormous distance before returning that energy. In fact, there's no limit on how far a virtual massless photon can go. This means the electromagnetic force has infinite range. Two charged particles will influence each other no matter how far apart they are. The force weakens with distance, falling off as one over the square of the distance between them, but it never reaches zero. It never cuts off. It extends across the entire observable universe. When you look up at a star thousands of light years away and see its light, real photons that were emitted from that star thousands of years ago have traveled across the immense vastness of space to reach your eye. The electromagnetic connection between charged particles stretches across the entire cosmos without limit. Second, the photon has a spin of 1. This makes it what physicists call a vector boson. The spin of the force carrier determines fundamental properties of the force it creates. Spin 1 bosons produce forces that can be both attractive and repulsive, depending on the charges of the particles involved. This is exactly what we observe with electromagnetism. Like charges repel each other, opposite charges attract. This duality, the ability to both push and pull, is a direct consequence of the photon being a spin-1 particle. If the photon had a different spin, the electromagnetic force would behave entirely differently. Third, the photon itself is electrically neutral. It carries no electric charge at all. This is important because it means photons don't interact directly with other photons through the electromagnetic force. Two beams of light can pass right through each other without affecting each other. You can cross two flashlight beams and they'll pass through one another without deflecting or scattering. This property makes the electromagnetic force relatively clean and simple compared to some of the forces. The force carrier doesn't interact with itself. As we'll discover later, this is not the case for all forces, and when the force carrier does interact with itself, the consequences are dramatic and strange. Fourth, there is only one type of photon. There's no positive photon or negative photon, no red photon or blue photon in the sense of carrying different types of charge. There's just the photon, a single type of force carrier for the entire electromagnetic interaction. This gives electromagnetism a certain beautiful simplicity. One force carrier, one type of charge with two signs, positive and negative, one elegant theory to describe it all. These properties of the photon, its zero mass, its spin of 1, its electrical neutrality, its uniqueness as a single type of particle, shape everything about the electromagnetic force. And the electromagnetic force in turn shapes almost everything you experience in daily life. When I say almost everything, I'm not exaggerating even slightly. Apart from gravity, virtually every force you encounter from the moment you wake up until the moment you fall asleep is electromagnetic in origin. When you push on a wall and it pushes back against your hand, that's the electromagnetic force. The electrons in the atoms of your hand and the electrons in the atoms of the wall are repelling each other through the exchange of virtual photons. When you sit in a chair and the chair supports your weight, electromagnetic forces between atoms in the chair material resist compression and prevent you from falling through. When you pick up a cup of coffee, friction between your fingers and the ceramic surface allows you to grip it. And friction is fundamentally an electromagnetic phenomenon arising from interactions between surface atoms. The tension in a rope that holds a climber is electromagnetic. The elasticity of a rubber band that snaps back when stretched is electromagnetic. The hardness of a diamond that resists being scratched is electromagnetic. The stickiness of tape, the slipperiness of ice, the strength of steel, the flexibility of rubber, every mechanical property of every material you have ever touched is determined by electromagnetic interactions between atoms. Chemistry itself is entirely electromagnetic. Every chemical reaction that has ever occurred, every bond that has ever formed between atoms, every molecule that has ever assembled, it's all driven by the electromagnetic force. Electrons in different atoms interact through virtual photon exchange, and these interactions determine which atoms bond with which other atoms, how strongly they bond, and in what geometric arrangements. The structure of DNA, the double helix that carries your genetic code, is held together by electromagnetic interactions between its atoms. The folding of proteins into their functional shapes is governed by electromagnetic forces between amino acids. The metabolic reactions that power every cell in your body are electromagnetic processes. Every single aspect of biology, from the firing of neurons in your brain, to the contraction of muscles in your arms, to the replication of your cells, is ultimately driven by electromagnetic interactions carried by virtual photons. Light itself is electromagnetic. Photons are both the carriers of the electromagnetic force and the particles of light. When you see anything at all, real photons enter your eye, strike the retina, and trigger electromagnetic chemical reactions that send electrical signals along your optic nerve to your brain. The warmth you feel from the sun is carried by infrared photons. The tan or sunburn you get is caused by ultraviolet photons interacting with your skin cells. Radio, television, Wi-Fi, cell phone signals, X-rays, microwaves. All of these are electromagnetic radiation, all carried by photons of different frequencies. Think about what this means. Almost every sensory experience you have ever had is the result of photon exchange at some level. Every color you've seen is carried by photons. Every texture you've touched is the result of electromagnetic interactions between your skin and the surface. Every sound you've heard is transmitted through the air by electromagnetic forces between air molecules pushing against your eardrum. The taste of food results from electromagnetic interactions between molecules and your taste receptors. The smell of flowers is carried by molecules whose shapes are determined by electromagnetic bonding, and whose detection by your nose involves electromagnetic interactions with receptor proteins. The photon, this massless spin-1 electrically neutral boson, is responsible for essentially the entire world of human experience. Without photons mediating the electromagnetic force, the universe would still contain matter. Quarks and electrons and neutrinos would still exist as excitations of their respective fields, but nothing would interact electromagnetically. There would be no force to bind electrons to nuclei, so atoms could not form. Without atoms, there would be no molecules. Without molecules, there would be no chemistry. Without chemistry, there would be no biology. Without biology, there would be no life. And without life, 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 there would be no one to look up at the sky and wonder how forces work. The success of QED set the template for all of modern particle physics. Once physicists saw that the electromagnetic force could be described with such extraordinary precision as the exchange of virtual photons within quantum field theory, they naturally asked the obvious next question. Could other forces be described the same way? Could there be other bosons, other force carriers, responsible for other forces? And if so, what properties would those bosons need to have to produce the specific forces we observe in nature? This question leads us somewhere unexpected, because everything we've talked about so far, all the extraordinary precision of QED, all the elegance of virtual photon exchange, all the forces you feel in everyday life, none of it can explain what's happening inside the heart of an atom. The electromagnetic force, for all its reach and power, is only one piece of the story. And when you zoom in past the electron cloud, past the orbiting charges, and look directly at the atomic nucleus, you find a world that plays by completely different rules. Rules that are stranger, more violent, and more beautiful than anything electromagnetism prepared you for. Think about what we've learned so far. The photon is massless, which gives electromagnetism infinite range. The photon is electrically neutral, which means it doesn't interact with itself. The photon is a single type of particle, which gives the electromagnetic force its elegant simplicity. These are the properties that define electromagnetism. They make it clean, well-behaved, and beautifully described by QED. But what if a force carrier wasn't massless? What if a force carrier did interact with itself? What if there were multiple types of force carriers for a single force, each carrying their own charge? What would a force look like then? How would it behave? Would it have infinite range, or would it be confined to a tiny region of space? Would it simply push and pull, or could it do something more radical, something no other force can do? These aren't hypothetical questions. They describe real forces that operate inside every atom in your body right now. Forces carried by bosons with properties so different from the photon that they create phenomena electromagnetism could never produce. One of these forces is so powerful that it makes electromagnetism look feeble by comparison. The other is so unusual that it doesn't just push or pull particles. It transforms them into entirely different particles, changing the fundamental identity of matter itself. Both of these forces are invisible in everyday life. You've never felt them. You've never directly observed their effects with your own senses. But without them, the atoms in your body could not exist. The sun could not shine. The elements that make up everything around you could never have been forged. These forces are hidden, but they are essential. And the bosons that carry them are unlike anything we've encountered so far. To understand them, we need to go inside the nucleus, and that's where things get truly strange. Let's go inside the nucleus, because this is where the universe gets truly strange. Everything we've talked about so far, the electromagnetic force, virtual, photon exchange, QED, all of that operates in a world that's at least somewhat familiar. You can feel electromagnetic forces. You can see light. You experience the consequences of photon exchange every second of every day. But the forces inside the nucleus are different. They operate at scales so small that nothing in your daily experience can prepare you for them. The nucleus of an atom is about 1 femtometer across. That's 1 quadrillionth of a meter. If an atom were the size of a football stadium, the nucleus would be a small marble sitting at the center of the field. And inside that marble, forces rage with an intensity that makes electromagnetism look gentle by comparison. Here's the problem. Consider a helium nucleus. It contains 2 protons and 2 neutrons. The 2 protons are both positively charged. They're sitting right next to each other, separated by roughly 1 femtometer. At that distance, the electromagnetic repulsion between them is enormous. You can calculate it. 2 protons separated by 1 femtometer experience an electromagnetic repulsive force of about 230 newtons. That might not sound like much, but remember, these are subatomic particles. For objects that are tiny, that force is colossal. It's trying to blast those protons apart with extreme violence. And this is just a helium nucleus with 2 protons. Consider a gold nucleus. It has 79 protons packed into a space only a few femtometers across. The electromagnetic repulsion in a gold nucleus is staggering. All those positive charges crammed together, all pushing against each other with immense force. By every electromagnetic calculation, that nucleus should explode. It should fly apart in a fraction of a second. Every nucleus in your body heavier than hydrogen should be violently unstable. But it's not. Nuclei are stable. Gold exists. Iron exists. Carbon and oxygen and nitrogen exist. You exist. Something is holding those protons together against the furious electromagnetic repulsion trying to tear them apart. And that something has to be extraordinarily powerful. It has to overwhelm the electromagnetic force at nuclear distances. It has to be the strongest force in nature. And it is. It's called the strong nuclear force, and at the distances inside a nucleus, it's about 100 times more powerful than electromagnetism. It grabs those protons and neutrons and binds them together with such ferocity that the electromagnetic repulsion simply cannot overcome it. The nucleus holds. The strong force is carried by a boson called the gluon. The name comes from glue because gluons literally glue the nucleus together. But gluons don't just hold protons and neutrons together. They do something more fundamental than that. They hold the protons and neutrons themselves together. Because protons and neutrons aren't elementary particles, they're composite objects. Each proton is made of 3 quarks, 2 up quarks, and 1 down quark. Each neutron is also made of 3 quarks, 2 down quarks, and 1 up quark. And those quarks are held together by gluons. The strong force operates through a type of charge called color charge. Now, this has absolutely nothing to do with actual colors. Physicists just needed a name for this property, and they chose colors because the mathematics worked out in a way that's loosely analogous to how colors combine. In electromagnetism, there are 2 types of charge, positive and negative. In the strong force, there are 3 types of charge. They're called red, green, and blue. Every quark carries one of these 3 color charges. And just as opposite electric charges attract in electromagnetism, color charges interact through gluon exchange in the strong force. But here's where things get fundamentally different from electromagnetism. Remember how the photon is electrically neutral? It carries no electric charge of its own. That means photons don't interact with each other electromagnetically. 2 beams of light pass through each other without any effect. This makes the electromagnetic force relatively clean and well-behaved. Gluons are completely different. Gluons themselves carry color charge. A gluon isn't neutral. It carries a combination of a color and an anticolor. When a gluon is exchanged between 2 quarks, it changes their colors. A red quark might emit a red anti-blue gluon and become a blue quark. The gluon travels to a blue quark, which absorbs it and becomes a red quark. The colors have swapped. The quarks have exchanged their color charges through gluon exchange, and the force between them has been transmitted. The fact that gluons carry color charge has a staggering consequence. Because gluons are themselves colored, they interact with other gluons. Gluons feel the strong force. Photons don't feel the electromagnetic force because they're electrically neutral. But gluons feel the strong force because they carry color charge. This means gluons can exchange other gluons between themselves. They can interact with each other, pull on each other, bind to each other. The force carriers themselves are subject to the very force they carry. This creates a level of complexity that simply doesn't exist in electromagnetism. In QED, photons transmit the force between charges, but photons themselves are passive. They don't interact with each other. In the strong force, the gluons aren't just messengers carrying information between quarks. They're active participants in the force. They contribute to it. They amplify it. They make it stronger. This self-interaction of gluons leads to one of the most bizarre properties of the strong force, a property that has no analog in electromagnetism. It's called asymptotic freedom, and it was discovered by David Gross, David Politzer, and Frank Wilczek in 1973, earning them the 2004 Nobel Prize in Physics. Asymptotic freedom means that the strong force behaves in exactly the opposite way from electromagnetism when it comes to distance. With the electromagnetic force, the closer two charged particles are, the stronger the force between them. As you pull them apart, the force weakens. It falls off with the square of the distance. Double the distance, the force drops to 1/4. This makes intuitive sense. Things that are closer interact more strongly than things that are far apart. But the strong force works backward. When quarks are very close together, practically on top of each other at extremely short distances, the strong force between them is actually weak. The quarks behave almost as if they're free particles, barely interacting at all. This is the asymptotic freedom part. At very short distances, quarks are asymptotically free, meaning the force approaches zero as the distance approaches zero. But as you try to pull quarks apart, as the distance between them increases, the strong force gets stronger, not weaker, stronger. The more you pull, the harder it pulls back. Imagine stretching a rubber band, except this rubber band gets stiffer the more you stretch it. With a real rubber band, eventually it snaps. But the strong force doesn't snap, at least not in the usual sense. It just keeps getting stronger and stronger as you increase the distance. This behavior comes directly from gluon self-interaction. When two quarks move apart, the gluon field between them doesn't spread out and weaken like the electromagnetic field does. Instead, because gluons interact with each other, they form a narrow tube of concentrated field energy between the quarks. Physicists call this a flux tube, or a color string. As the quarks move apart, this tube stretches, but it doesn't thin out. It maintains this intensity, and the energy stored in the tube increases with its length. The farther apart the quarks get, the more energy is stored in the gluon field between them. At some point, there's so much energy in the stretched gluon tube that something dramatic happens. The energy becomes sufficient to create new quarks from the vacuum. Remember, energy and mass are interchangeable according to Einstein's famous equation. When the energy in the gluon tube reaches a critical threshold, it converts into mass. specifically into a new quark-antiquark pair that pops into existence in the middle of the tube. The tube breaks, but each broken end now has a quark attached to it. Instead of freeing the original quarks, you've just created new quarks. The original quarks are still bound. They've just found new partners. This is confinement. Quarks can never be isolated. You can never pull a single quark free from a proton or neutron and hold it up for examination. Every time you try, every time you pump in enough energy to separate quarks, that energy creates new quarks that immediately bind to the ones you were trying to free. The quarks always end up in groups. Specifically, they end up in groups of 3, like protons and neutrons, which physicists call baryons, or in pairs of a quark and an antiquark, which are called mesons, but never alone. Never a single isolated quark, not ever. No experiment has ever observed a free quark, and the theory of the strong force, quantum chromodynamics or QCD, explains exactly why. The gluon self-interaction creates confinement, which keeps quarks permanently imprisoned inside composite particles. This is spectacularly different from electromagnetism. You can easily isolate electric charges. You can have a free electron or a free proton sitting by itself in space, carrying its electric charge, interacting electromagnetically with anything that comes near it. But you can never have a free quark sitting by itself, carrying a color charge. The strong force forbids it. Confinement is absolute, and it all traces back to one crucial property of the gluon. The gluon carries color charge. The force carrier interacts with itself, and the self-interaction changes everything about how the force behaves. Because gluons carry color charge, the mathematics of the strong force is far more complex than the mathematics of electromagnetism. In QED, there's one type of photon. In QCD, there are 8 different types of gluons, each carrying a different combination of color and anti-color charges. Each of these 8 gluons can interact with each other as well as with quarks. The Feynman diagrams for QCD are much more complicated than those for QED. You still have the basic diagram of 2 quarks exchanging a gluon. But you also have diagrams where gluons split into 2 gluons, where 3 gluons interact at a single vertex, where 4 gluons interact at a single vertex, where gluons form loops and interact with themselves in complex ways. All of these diagrams contribute to the strong force, and because the force gets stronger at larger distances rather than weaker, the perturbative techniques that work so beautifully in QED, calculating simple diagrams first and adding corrections from more complex ones, don't work as well in QCD at low energies and large distances. At these scales, all the diagrams are important. None of them are small corrections. This makes QCD calculations extremely difficult. Physicists often have to use enormous computer simulations called lattice QCD, where they model space itself as a grid of points and calculate the strong force numerically to get results for low-energy strong force physics. Despite these computational challenges, QCD has been tested extensively and has passed every test. The theory correctly predicts the masses of protons and neutrons. Remember, protons and neutrons are made of quarks, but the quarks themselves contribute only about 1% of the proton's mass. The rest, roughly 99% of the mass of a proton, comes from the energy of the gluon field binding the quarks together. The kinetic energy of quarks bouncing around inside the proton and the potential energy stored in the gluon field that confines them contribute the overwhelming majority of the proton's mass. Since protons and neutrons make up essentially all the mass of ordinary matter, this means that roughly 99% of the mass of everything around you, your body, the ground beneath your feet, the air you breathe, comes from the energy of the strong force, from gluon fields holding quarks together. Only about 1% comes from the intrinsic masses of the quarks themselves. When you step on a scale and read your weight, 99% of that weight is gluon field energy. You are, in a very real sense, made mostly of force. Now let's turn to the third force operating inside the nucleus, the weak nuclear force. And the weak force is genuinely bizarre. It does something that no other force in the universe can do. It changes the identity of particles. The electromagnetic force pushes and pulls charged particles. The strong force binds quarks together. But neither of them can turn one type of particle into another type. The weak force can. It can reach into a neutron, change one of its down quarks into an up quark, and transform the neutron into a proton. In doing so, it creates an electron and an antineutrino that fly away carrying the excess energy. This process is called beta decay, and it's one of the most important processes in the universe. The weak force is carried by 3 bosons: the W plus boson, the W minus boson, and the Z boson. The W stands for weak. The Z doesn't stand for anything specific. It was just the next letter after W. These 3 bosons are strikingly different from the photon and the gluon in one critical respect. They're massive. Extremely massive. The W bosons have a mass of about 80.4 gigaelectron-volts divided by c squared. The Z boson is even heavier at about 91.2 gigaelectron-volts divided by c squared. To put this in perspective, a proton has a mass of about 0.938 gigaelectron-volts divided by c squared. The W boson is about 86 times heavier than a proton. The Z boson is about 97 times heavier than a proton. These are among the heaviest fundamental particles known. This mass has a direct and dramatic consequence for the weak force's range. Remember the principle we discussed with the photon. The mass of the force-carrying boson determines the range of the force. A massless boson can travel unlimited distances, giving the electromagnetic force infinite range. A massive boson needs to borrow energy to exist, and the more massive it is, the more energy it needs to borrow, the less time the uncertainty principle allows it to exist, and the shorter the distance it can travel. The W and Z bosons are so massive that the energy they need to borrow is enormous. They can only exist for an incredibly brief time. They can only travel an incredibly short distance before they must vanish. That distance is approximately 0.001 femtometers, 1,000th of 1 quadrillionth of a meter. About 1,000 times smaller than a proton. The weak force only operates across distances smaller than an atomic nucleus. Beyond that distance, it simply doesn't reach. This is why the weak force is weak. Not because the fundamental interaction is intrinsically feeble, but because the massive W and Z bosons can only travel such tiny distances. At extremely close range, the weak force is actually comparable in strength to the electromagnetic force. But because its range is so tiny, its effects are confined to the subatomic world. The W bosons are special because they carry electric charge. The W plus carries a positive charge and the W minus carries a negative charge. This is unique among force carriers. Photons are neutral. Gluons carry color charge but not electric charge. The W bosons carry actual electric charge, which means they interact electromagnetically as well as through the weak force. When a W boson is exchanged between two particles, it transfers electric charge from one to the other. This is how the weak force changes particle identities. A down quark with a charge of -1/3 emits a W- boson and becomes an up quark with a charge of +2/3. The W- boson then decays into an electron and an antineutrino. The charge is conserved throughout the process, but the quark's identity has changed. It was a down quark, and now it's an up quark. The weak force has performed a transformation that no other force can accomplish. The Z boson, by contrast, is electrically neutral. It mediates what are called neutral current interactions, where particles interact through the weak force without changing their identity or charge. Two neutrinos can scatter off each other by exchanging a Z boson, for example. Neutral current interactions are subtler than charged current interactions, but they were just as real and just as important for the complete picture of the weak force. Why does any of this matter? Why should you care about a force that only operates at distances smaller than a proton? Because the weak force is responsible for some of the most important processes in the entire universe. First, the weak force powers the sun. Deep in the sun's core, hydrogen nuclei are being fused into helium. This is the process that generates the energy that warms our planet, drives weather systems, fuels photosynthesis, and makes life possible. But the first step of this fusion chain requires the weak force. Two protons need to fuse together, but two protons can't just form a stable nucleus. Two positive charges repelling each other with no neutron to help bind them. For the process to work, one of the protons needs to transform into a neutron during the collision. And the only force that can do this is the weak force. One of the protons emits a W+ boson, which changes one of its up quarks to a down quark, transforming it into a neutron. The W+ boson then decays into a positron and a neutrino. The proton and the newly created neutron bind together to form a deuterium nucleus, and the fusion chain continues from there. This step, this weak force step, is actually the bottleneck of the entire fusion process. It's incredibly unlikely for the weak force to trigger this transformation in any given proton collision, because the range is so short and the probability is so low. Protons in the sun's core collide with each other billions of times before the weak force finally manages to convert one of them into a neutron. This is actually a good thing, because it means the sun burns its fuel very slowly. If the weak force was stronger or had a longer range, the sun would burn through its hydrogen much faster and wouldn't last long enough for life to evolve. The weakness of the weak force is what makes the sun a long-lived stable star that has been burning steadily for 4.6 billion years and will continue for another 5 billion. Second, the weak force is responsible for radioactive beta decay. When an unstable nucleus has too many neutrons, the weak force can convert one of those neutrons into a proton, emitting an electron and an antineutrino in the process. This is beta minus decay. When a nucleus has too many protons, the weak force can convert a proton into a neutron, emitting a positron and a neutrino. This is beta plus decay. These processes are essential for nuclear physics. They determine which isotopes are stable and which are radioactive. They determine the rates of radioactive decay that are used in medical imaging, cancer treatment, carbon dating, and nuclear power. Third, the weak force played a crucial role in the early universe. In the first few minutes after the Big Bang, The weak force helped determine the ratio of protons to neutrons in the cosmos. This ratio in turn determined how much hydrogen and helium formed during Big Bang nucleosynthesis, which set the initial chemical composition of the entire universe. If the weak force had different properties, the hydrogen to helium ratio would be different, stars would burn differently, and the universe might not have produced the elements necessary for life. Fourth, the weak force is the only force that interacts with neutrinos. Neutrinos are ghostly particles that have almost no mass and interact with matter only through the weak force and gravity. Because the weak force is so feeble and short-ranged, neutrinos can pass through essentially anything. Billions of neutrinos from the sun pass through your body every single second, and virtually none of them interact with any of your atoms. A neutrino could pass through a wall of LED a light year thick and still have a good chance of making it through without hitting anything. The only reason we can detect neutrinos at all is because we build enormous detectors, thousands of tons of material, and wait patiently for the extremely rare occasions when a neutrino happens to interact with an atom through the weak force. Now, let's step back and look at all three forces together, because the contrast between them reveals something deep about how the universe is structured. Electromagnetism is carried by the photon, which is massless, electrically neutral, and doesn't interact with itself. This gives electromagnetism infinite range, both attractive and repulsive behavior depending on charges, and relatively simple mathematical structure. The strong force is carried by gluons, which are massless but carry color charge and interact powerfully with themselves. This self-interaction gives the strong force its unique character, asymptotic freedom at short distances and confinement at larger distances. Quarks can never be isolated. This strong force has a finite effective range of about 1 femtometer, not because gluons are massive, but because confinement prevents the force from extending beyond the boundaries of composite particles. The weak force is carried by the W and Z bosons, which are extremely massive. Their mass limits the weak force to an incredibly short range of about 0.001 femtometers. The W bosons carry electric charge, which allows the weak force to change particle identities, something no other force can do. The Z boson is neutral and mediates more subtle interactions. 3 forces, 3 sets of bosons, 3 completely different behaviors, and all of them working together to create the universe you see around you. The electromagnetic force builds atoms by binding electrons to nuclei. The strong force builds nuclei by binding quarks into protons and neutrons, and then binding protons and neutrons together. The weak force enables stellar fusion by transforming protons into neutrons, powering the stars that forge heavy elements and fill the universe with light and warmth. Remove any one of these forces and the universe collapses. Without electromagnetism, no atoms. Without the strong force, no nuclei heavier than hydrogen, no complexity, no chemistry beyond the most basic. Without the weak force, no stellar energy, no mechanism for stars to shine, no heavy elements scattered into space by supernova explosions for later generations of stars and planets to use. But here's a puzzle that haunted physicists for decades. The photon is massless. Gluons are massless. So why are the W and Z bosons so heavy? What gives them their enormous mass? And why does mass matter so much for these particular bosons when the other force carriers manage just fine without it? This question, the question of where mass comes from, is one of the most profound questions in all of physics. Because mass doesn't just affect the W and Z bosons, it affects almost every particle in the universe. Electrons have mass, quarks have mass, the W and Z bosons have mass, and the mechanism that gives them all their mass is one of the most beautiful and subtle ideas in modern physics. It involves a field that fills all of space, a field that every massive particle interacts with as it moves, a field whose existence was predicted decades before it was confirmed, and whose discovery required the largest and most complex machine ever built by the human species. That field is the Higgs field, and the boson associated with it, the Higgs boson, is the final piece of the puzzle that explains why forces work the way they do, and why the universe has the structure it has. So we've arrived at the deepest question in this entire story. Why are some bosons massive and others massless? The photon has no mass at all, gluons have no mass, but the W and Z bosons are among the heaviest fundamental particles ever discovered. The W boson is about 86 times heavier than a proton. The Z boson is about 97 times heavier. This isn't a minor detail. This enormous mass is what confines the weak force to distances smaller than an atomic nucleus. It's what makes the weak force weak. If the W and Z bosons were massless like the photon, the weak force would have infinite range, just like electromagnetism. It would be a long-range force affecting the entire universe. The behavior of matter at every scale would be completely different. Chemistry would be different. Stars would be different. Life, if it could exist at all, would be unrecognizable. So where does this mass come from? Why do the W and Z bosons have mass while the photon doesn't? For decades, this was one of the most important unanswered questions in physics. And the answer, when it finally came, turned out to be one of the most beautiful and strange ideas in the history of science. The answer is the Higgs field. To understand the Higgs field, we need to go back to a puzzle that emerged in the 1960s. Physicists have been working on theories to unify the electromagnetic force and the weak force into a single framework. This might sound surprising. Electromagnetism and the weak force seem completely different. One has infinite range, the other is confined to subatomic distances. One is carried by a massless photon, the other by massive W and Z bosons. One preserves particle identities, the other changes them. How could these possibly be the same force? But there were hints. Deep mathematical similarities between the two forces suggested they might be related. The way the forces coupled to particles, the mathematical structure of their interactions, the symmetries they obeyed, all of these pointed toward a deeper connection. Physicists suspected that electromagnetism and the weak force were actually two aspects of a single unified force, the electroweak force. At very high energies, the kind of energies that existed in the first fraction of a second after the Big Bang, this unified force would look like one thing. But at the lower energies we experience today, it splits into two seemingly different forces, electromagnetism and the weak force. The problem was mass. The mathematical framework that described this unification required all the force-carrying bosons to be massless. The symmetry of the theory demanded it. If you wrote down the equations for the electroweak force with perfect symmetry, all four bosons, the photon, the W+, the W-, and the Z would have to be massless. But we know that's not true. The W and Z bosons are extremely massive. So something had to be breaking the symmetry. Something had to be giving mass to the W and Z bosons while leaving the photon massless. Something had to be taking this perfectly symmetric theory and making it lopsided, breaking it in exactly the right way to produce the universe we observe. In 1964, several physicists independently proposed a mechanism that could do exactly this. Peter Higgs, Robert Boruth, and Francois Engler, along with other theorists including Gerald Guralnick, Carl Hagen, and Tom Kibble, all published papers describing what we now call the Higgs mechanism. The key idea is extraordinarily elegant. What if there's a field that fills all of space, every cubic centimeter of the universe, from here to the most distant galaxy? Not an electromagnetic field or a strong force field, but a completely new type of field. A field that interacts with certain particles and not others. A field that is always there, always on, always present, even in what we think of as completely empty space. This field is the Higgs field. Now, the crucial property of the Higgs field is that unlike most other quantum fields, the Higgs field has a non-zero value everywhere. Most quantum fields, in their lowest energy state, their ground state, have a value of 0. The electromagnetic field in empty space, far from any charges, is 0. It's calm, undisturbed, quiet. But the Higgs field is different. Its lowest energy state is not 0. Even in the emptiest void of space, the Higgs field has a specific non-zero value. It's always turned on. It pervades everything. You're immersed in it right now. Every atom in your body is swimming through the Higgs field at this very moment. You can't escape it. There's nowhere in the universe where the Higgs field is 0. This non-zero background value of the Higgs field is what gives particles their mass. Here's how it works. When a particle moves through the Higgs field, it can interact with that field. If it interacts strongly, it experiences a lot of resistance, a lot of drag, a lot of inertia. That resistance is what we call mass. A particle that interacts very strongly with the Higgs field has a large mass. A particle that interacts weakly with the Higgs field has a small mass. And a particle that doesn't interact with the Higgs field at all has 0 mass. Let me use an analogy that might help, even though, like all analogies for quantum physics, it's imperfect. Imagine a room full of people at a party. The room is the Higgs field. Now imagine a celebrity walks into the room. Everyone clusters around them, slowing them down, making it hard for them to move. They feel heavy, sluggish, difficult to accelerate. That's a particle with a lot of mass. It interacts strongly with the Higgs field and experiences a lot of resistance. Now imagine an unknown person walks into the same room. Nobody pays attention. Nobody clusters around them. They glide through effortlessly. That's a particle with very little mass. It barely interacts with the Higgs field. And imagine someone who is somehow invisible, who doesn't interact with the partygoers at all. They pass straight through the room without any resistance. That's a massless particle like the photon. The W and Z bosons interact strongly with the Higgs field. That's why they're so massive. The photon doesn't interact with the Higgs field at all. That's why it's massless. And this distinction, this difference in how strongly different particles interact with the Higgs field, is what breaks the symmetry of the electroweak force. At the deepest level, the electroweak theory starts out perfectly symmetric. All 4 bosons are identical and massless. But the Higgs field, with its non-zero background value everywhere in space, breaks that symmetry. It gives mass to 3 of the 4 bosons, the W+, the W-, and the Z, while leaving the 4th one, the photon, massless. This spontaneous symmetry breaking is what splits the unified electroweak force into the 2 forces we observe today. The long-range electromagnetic force mediated by the massless photon, and the short-range weak force mediated by the massive W and Z bosons. The concept of spontaneous symmetry breaking comes from condensed matter physics, from the study of how materials behave at different temperatures. Think about a magnet. At high temperatures, the atoms in a piece of iron are jiggling around randomly. Their tiny magnetic fields point in all directions. The material has a perfect symmetry because no direction is special. But when you cool the iron below a certain temperature, called the Curie temperature, something happens. The atoms suddenly align. Their magnetic fields all point in the same direction, and the material becomes magnetized. The symmetry is broken. One direction has become special even though the underlying laws of physics treat all directions equally. The Higgs mechanism works in a similar way but applied to particle physics. The underlying laws of the electroweak theory treat all four bosons equally. But the Higgs field, like the aligned atoms in a magnet, has settled into a state that breaks that symmetry, giving mass to some bosons and not others. Now, the Higgs field is a quantum field, just like all the other fields we've discussed. And just like other quantum fields, it can be excited. It can be disturbed. And when you excite it enough, when you pump enough energy into it, you create a particle. The particle associated with excitations of the Higgs field is the Higgs boson. The Higgs boson is to the Higgs field what the photon is to the electromagnetic field. It's the quantum, the smallest possible excitation, the particle manifestation of the field. But here's the thing. The Higgs boson is incredibly difficult to create. It's extremely massive, about 125 giga-electron volts divided by c squared, roughly 133 times heavier than a proton. To create a Higgs boson, you need to concentrate an enormous amount of energy into a tiny space. You need particle collisions at energies far beyond what any natural process on Earth can produce. You need the most powerful machine ever built by human beings. That machine is the Large Hadron Collider, or LHC, located at CERN near Geneva, Switzerland. The LHC is a circular tunnel about 27 kilometers in circumference, buried underground beneath the Swiss-French border. Inside this tunnel, two beams of protons are accelerated to nearly the speed of light, traveling in opposite directions. These protons are pushed faster and faster by powerful, superconducting magnets cooled to temperatures colder than outer space, about 1.9 degrees above absolute zero. When the protons reach their maximum energy, they're directed into each other. The protons smash together at combined energies of 13 tera electron volts, recreating conditions that haven't existed naturally since a fraction of a second after the Big Bang. The scale of this machine is difficult to comprehend. The tunnel sits between 60 and 170 meters underground. The proton beams travel around the ring about 11,000 times per second. At full operation, each beam contains around 300 trillion protons organized into tightly packed bunches. When two bunches cross paths at one of the collision points, roughly 600 million proton collisions happen every single second. The amount of data generated is so enormous that even the most powerful computers on Earth cannot record all of it. Sophisticated filtering systems decide in real time which collisions might be interesting enough to save and which can be discarded. Only about 1 in every million collision events is actually recorded for later analysis. The rest are lost forever. Building the LHC took over a decade and involved more than 10,000 scientists and engineers from over 100 countries. The superconducting magnets that steer the proton beams are among the most precise instruments ever manufactured. Each magnet must produce fields accurate to within a fraction of a percent, because even tiny imperfections would cause the beams to drift and miss each other. The entire ring must be aligned to tolerances measured in fractions of a millimeter across a circumference of 27 kilometers. Cooling the magnets to 1.9 degrees above absolute zero requires the largest cryogenic system on the planet. The engineering challenges were so extreme that many experts doubted the machine could be built at all. But it was built, and it worked. And when it reached full power, it became the most powerful microscope ever created, not by magnifying small things, but by smashing particles together with such energy that the debris revealed structures and fields hidden far below the scale of atoms. In these collisions, the concentrated energy can excite the Higgs field and produce Higgs bosons. But the Higgs boson is fantastically rare. Only about 1 in every 10 billion proton collisions produces a Higgs boson. And the Higgs boson itself is incredibly short-lived. It exists for about 1.6 times 10 to the negative 22 seconds before it decays into other particles. You never see the Higgs boson directly. You only see the debris it leaves behind when it decays, and you have to sift through billions upon billions of collision events to find the handful that show the distinctive signature of a Higgs boson creation and decay. On July 4th, 2012, physicists at CERN announced that they had found it. 2 independent detector teams, the LHC called ATLAS and CMS, each with thousands of scientists from dozens of countries, had independently observed a new particle with properties consistent with the Higgs boson. The mass was about 125 giga-electron-volts divided by c squared. The spin was 0, exactly as predicted. The decay patterns matched theoretical expectations. After nearly 50 years of searching, the Higgs boson had been found. Peter Higgs and François Englert were awarded the 2013 Nobel Prize in Physics for their theoretical prediction of this mechanism. Robert Brute, who had worked with Englert on the original theory, had passed away in 2011 and didn't live to see the discovery confirmed. The discovery of the Higgs boson was one of the greatest triumphs in the history of science. It confirmed a theoretical prediction made nearly half a century earlier. It validated the mechanism by which particles acquire mass. It completed the standard model of particle physics, the theoretical framework that describes all known fundamental particles and 3 of the 4 known forces. Every particle predicted by the standard model had now been observed. Every force carrier had been detected. The theory was complete. But the Higgs boson also stands apart from the other bosons we've discussed. The photon, the gluon, and the W and Z bosons are all force carriers. They mediate interactions between matter particles. They carry forces. The Higgs boson doesn't carry a force in the traditional sense. It's not exchanged between particles to create pushes or pulls like the other bosons. Instead, it's the manifestation of the field that gives particles their mass. It's the proof that the Higgs field exists. It's the smoking gun that confirms the mechanism by which the electroweak symmetry is broken and particles acquire the masses they have. The Higgs boson has spin 0, making it what physicists call a scalar boson. All the other bosons we've discussed have spin 1, making them vector bosons. The Higgs boson is fundamentally different in character. It's not a force carrier in the way photons and gluons are. It's something else entirely. It's the particle that explains why force carriers have the properties they do, why some are massive and others aren't, why the forces of nature have the ranges and strengths we observe. It is also worth understanding what the Higgs field does not explain. The Higgs mechanism gives mass to the W and Z bosons, and it gives mass to fundamental fermions like electrons and quarks. But it doesn't give mass to protons and neutrons. Remember, about 99% of the mass of a proton comes from the energy of the gluon field binding its quarks together, not from the intrinsic masses of the quarks themselves. The Higgs field gives each up quark a mass of only about 2.2 mega electron volts, and each down quark a mass of about 4.7 mega electron volts. But a proton made of 2 up quarks and 1 down quark has a mass of about 938 mega electron volts. The overwhelming majority of that mass comes from the strong force energy holding it together, not from the Higgs mechanism. So when people say the Higgs boson explains where mass comes from, that's partially true. It explains where the fundamental masses of elementary particles come from. But most of the mass you experience in daily life, the mass of your body, the mass of the chair you're sitting in, the mass of the Earth, comes from gluon field energy, not from the Higgs field. Now, you might have noticed that we've discussed 3 forces tonight: electromagnetism, the strong force, and the weak force. But there are 4 known forces in nature. The 4th is gravity. And gravity is conspicuously absent from everything we've talked about. There's a reason for that. Gravity doesn't fit into the standard model. If gravity followed the same pattern as the other forces, it would be carried by a boson called the graviton. The graviton would be massless, explaining gravity's infinite range. It would have a spin of 2, which would make it a tensor boson rather than a vector boson like the photon. A spin 2 force carrier produces a force that is always attractive, never repulsive. This matches what we observe about gravity. It only attracts, it never repels. 2 masses always pull toward each other. They never push apart. The mathematical properties of a spin 2 massless boson match the observed properties of gravity remarkably well. But here's the problem. We've never detected a graviton, not one, and we may never be able to. Gravity is extraordinarily weak compared to the other forces. At the scale of individual particles, gravity is about 10 to the 36th power times weaker than electromagnetism. That's a 1 followed by 36 zeros times weaker. A single graviton would carry so little energy that detecting it would require a detector so sensitive that, according to some calculations, it would need to be larger than the observable universe. The graviton, if it exists, may be forever beyond our ability to observe directly. There's a deeper problem too. When physicists try to apply the techniques of quantum field theory to gravity, the calculations break down. The theory produces infinities that can't be tamed by renormalization, the technique that works so brilliantly for QED and the other forces. Gravity resists being quantized. It doesn't fit into the same mathematical frameworks that describes the other 3 forces so beautifully. This suggests that our understanding of gravity is incomplete. Einstein's general theory of relativity describes gravity not as a force carried by a particle, but as a curvature of space-time caused by mass and energy. According to general relativity, the Earth doesn't pull you downward with a force. Instead, the Earth's mass warps the space-time around it, and you follow the curvature of that warped space-time, which happens to lead toward the center of the Earth. This geometric picture of gravity is extraordinarily successful. It predicted the bending of light by gravity, the existence of gravitational waves, the behavior of black holes, and the expansion of the universe, all confirmed by observation. But it's fundamentally incompatible with quantum mechanics. General relativity is a classical theory. It treats space-time as smooth and continuous. Quantum mechanics says everything is discrete, quantized, probabilistic. Combining the two into a quantum theory of gravity is one of the greatest unsolved problems in physics. String theory, loop quantum gravity, and other approaches have been proposed, but none has been experimentally confirmed. We simply don't know how gravity works at the quantum level. And gravity isn't the only mystery. The Standard Model, for all its success, leaves enormous questions unanswered. Dark matter makes up about 27% of the total energy content of the universe. We know it exists because we can measure its gravitational effects on galaxies and galaxy clusters. Stars in galaxies orbit faster than they should if only visible matter were present. Galaxy clusters are held together by more gravity than visible matter can account for. The cosmic microwave background radiation shows patterns that can only be explained if dark matter exists. But none of the particles in the Standard Model can be dark matter. Whatever dark matter is, it's something new. Something outside our current theory. It doesn't interact through electromagnetism, or it would be visible. It doesn't interact through the strong force, or we'd detect it in nuclear physics experiments. It might interact through the weak force, or through gravity, or through some entirely new force we haven't discovered yet. There might be dark matter bosons, dark force carriers, mediating interactions we know nothing about. An entire shadow physics could exist, hidden from our instruments with its own particles, its own forces, and its own bosons that we've never detected. Then there's dark energy, making up about 68% of the universe's energy content. Dark energy is causing the expansion of the universe to accelerate. We have almost no understanding of what it is. It could be a property of space itself. It could be a new quantum field with its own excitations. It could be something entirely outside our current theoretical frameworks. There's also the hierarchy problem. The Higgs boson has a mass of about 125 giga-electron volts. But quantum corrections from virtual particles should push that mass up to the Planck scale, about 10 to the 19th giga-electron volts, which is roughly 10 to the 17th times larger. The fact that the Higgs mass is so much smaller than this natural scale requires an incredible fine-tuning of the theory's parameters. It's as if you balanced a pencil perfectly on its tip. It's possible, but it demands explanation. Why is the Higgs mass so small compared to where the mathematics says it should be? Supersymmetry was proposed as a solution, positing that every known particle has a heavier partner particle, and these partner particles would cancel out the quantum corrections that inflate the Higgs mass. But the LHC has searched for supersymmetric particles and found nothing so far. If supersymmetry exists, the partner particles are heavier than our current experiments can reach. And finally, there's the question of unification. We've seen how the electromagnetic force and the weak force are actually two aspects of a single electroweak force, unified by the Higgs mechanism. Could the strong force also be unified with the electroweak force? Could all three quantum forces be different manifestations of a single underlying force? Grand unified theories, or GUTs, propose exactly this. They suggest that at extremely high energies, far beyond what any particle accelerator can reach, all three forces merge into one. Some GUTs predict that protons should eventually decay, though with a half-life of something like 10 to the 36th years, vastly longer than the age of the universe. Experiments have been searching for proton decay for decades but haven't found it yet. Could gravity also be included in this unification? A theory that unifies all four forces, sometimes called a theory of everything, remains the ultimate goal of theoretical physics. String theory is one candidate, but it requires extra dimensions of space that we've never observed, and it makes very few testable predictions. We're still searching. But let's step back now and look at the full picture, because what we've uncovered tonight is extraordinary. We started with a simple question: what is a boson, and why do forces exist? And the answer has taken us on a journey through the deepest levels of reality. Forces exist because particles exchange bosons. That's the mechanism. Two electrons repel each other because they exchange virtual photons. Quarks bind together inside protons because they exchange gluons. A neutron can transform into a proton because the weak force exchanges W bosons between quarks. And all of this happens within quantum fields, invisible structures that fill every point in space, and whose excitations are the particles we observe. The universe isn't made of stuff sitting in empty space. There is no empty space. Space is filled with fields. The electromagnetic field, the strong force field, the weak force field, the Higgs field, the electron field, the quark fields, the neutrino fields, all layered on top of each other, permeating every cubic centimeter of existence. What we call particles are ripples in these fields. What we call forces are interactions between these fields. What we call mass is the interaction between particles and the Higgs field. Everything you see, everything you feel, everything you experience, from the light entering your eyes to the chair supporting your weight, to the nuclear reactions powering the sun that warms your planet, all of it is the result of quantum fields interacting through the exchange of bosons. Every force you have ever felt is a conversation. The electromagnetic force is a conversation between charged particles, conducted through the exchange of virtual photons. The strong force is a conversation between quarks, conducted through the exchange of gluons. The weak force is a conversation that can change the very identity of the speakers, conducted through the exchange of W and Z bosons. And the Higgs field provides the stage, giving mass to the actors and shaping how the entire drama unfolds. Think about what that means for you. Right now, in your body, roughly 7 billion atoms are engaged in these conversations simultaneously. Photons are being exchanged between electrons and nuclei, holding your atoms together. Gluons are raging inside every proton and neutron in every nucleus, binding quarks with ferocious intensity. The Higgs field is giving mass to every electron and every quark, ensuring that your atoms have the properties they need to form molecules, cells, and tissues. And deep inside every star you see in the night sky, the weak force is quietly converting protons into neutrons, releasing the energy that makes those stars shine. You're not separate from these forces. You're made of these forces. The atoms in your body are held together by bosons. The nuclei in those atoms are bound by bosons. The mass of those atoms comes from interactions with a boson field. You are, quite literally, a structure built from the exchange of invisible messenger particles within quantum fields. Everything you have ever touched, seen, heard, tasted or smelled is the result of bosons doing their work. And here's what's perhaps most remarkable of all. We figured this out. Human beings, made of atoms, made of quarks and electrons, made of quantum field excitations, managed to discover the rules governing their own existence. We peeled back the layers of reality from the everyday world of pushes and pulls to the quantum world of virtual particles and field excitations, and we found a picture of extraordinary beauty and precision. A picture where forces aren't mysterious influences acting at a distance, but conversations between particles conducted through the elegant language of boson exchange. The universe is not a collection of objects. It's a web of interactions. It's fields talking to fields, particles exchanging particles, forces emerging from conversations that happen trillions of times per second in every atom of everything that exists. And at the heart of every one of those conversations is a boson, a tiny messenger born from a quantum field, carrying force from one piece of matter to another, and vanishing before anyone could ever directly see it. You can't see these messengers. You can't touch them. You can't isolate them. But you can feel their effects in every force that holds you together, and every force that holds the universe together around you. The photon connects charged particles across the breadth of the cosmos with a force that never ends. The gluon binds the hearts of atoms with a grip that can never be broken. The W and Z bosons quietly transform the nature of matter itself, powering the stars and shaping the elements. And the Higgs field, silent and invisible, fills every corner of existence, giving substance to particles that would otherwise be as weightless as ghosts. That's what a boson really is. It's the reason forces exist. It's the mechanism behind every interaction in the universe. It's the answer to the question that puzzled Newton when he wondered how the sun could reach across millions of miles of empty space and hold the Earth in its orbit. The space isn't empty. It's filled with fields, and the forces aren't mysterious. They're the result of particles exchanging bosons within those fields. The next time you feel the warmth of sunlight on your skin, remember what's happening. Photons, excitations of the electromagnetic field, are traveling 93 million miles from the sun and being absorbed by the atoms in your skin. The next time you stand on solid ground, remember that the ground feels solid because electrons in your feet and electrons in the floor are exchanging virtual photons and refusing to occupy the same space. The next time you look up at a star and wonder what makes it shine, remember that deep in its core, the weak force is slowly converting protons into neutrons, releasing the energy that has traveled for thousands or millions of years to reach your eye as a point of light in the darkness. Every force you have ever felt is a boson doing its job. Every structure you have ever seen is held together by bosons. Every moment of your existence depends on the ceaseless, tireless exchange of these invisible messengers within the quantum fields that make up the deepest fabric of reality. You are, in every meaningful sense, a child of the bosons, born from their interactions, sustained by their exchanges, and made possible by the elegant, simple, profound mechanism of force through particle exchange. The universe is a conversation, and the bosons are the words,